This is embedded system project presentation which had been done as per the requirements. I, Nimra Areeb, have completed this assigned project of Tachometer with my classmates mentioned here. The basic purpose of this project is to implement all the concepts we learned throughout the semester. By only learning, it's not possible to have wide knowledge of things till we implement it. By working on hardware as well as software, we will discover the working of different devices. We will came to know about different components, their construction, and how are they used. So this embedded system project helped us discover working of different devices in daily life using coding and their applications. We implemented all this project on Texas instrument Tiva. So basically the project tachometer is a device that measures rotational speed of any shaft or disc, usually measured in RPM or radian. It is used in different digital devices like automotive car engines, washing machines, aircraft, and even in medical technology called hematachometer to know the blood flow rate.
The components which we have used in our project are Tiva microcontroller, 4x4 keypad, NIMA 17 stepper motor, A4988 stepper motor driver module, IR sensor, and 16x2 LCD display. Along with these components, we have used some other components like capacitors, potentiometers, breadboard, push button, jumper wires. Now we will discuss all of these components one by one. First of all, Tiva microcontroller. TM4C123G Launchpad Evaluation Kit is a low-cost evaluation platform for ARM Cortex M4 based microcontrollers. It has 6 GPIO ports such as port A, port B, port C, port D, and port E. 40 stackable header pins provide the interface to connect plug-in modules and make it easy and simple to expand the functionality of the TM4C123G Launchpad. The diamond-shaped platform hardware has 64 pins, out of which 43 are GPIO pins. Now we will discuss NIMA 17 stepper motor. Stepper motors are DC brushless and synchronous motors in low-speed devices which require smart rotatory movement at a specific speed without missing any single step can use the NIMA 17. In NIMA 17, all pins are connected internally in pairs, in two pairs, green and black pair, and the second pair will be of red and blue. It has some specifications like its rated voltage is 12 volt, phase current is 2.2 ampere, one step angle will be of 1.8 degree, total steps of each resolution will be 200, number of phases are 4. Now we will discuss stepper motor driver, which is A4988. A4988 driver has total 16 pins. First of all, VDD and ground is used for driving the internal logic circuit, which can be of 3 volt to 5.5 volt. V mode and ground supplies power for motor, which can be of 8 volt to 35 volt. Next we have MS1, MS2 and MS3. By setting appropriate logic levels to these three pins, we can set the motors to one of the 5 steps resolutions, which is full mode, half mode, quarter mode, eighth mode or 16th mode. Next we have step input pin controls the micro steps of motor. Next, direction input controls the spinning direction of motor. Enable pin is active low input. When pulled low logic 0, the A4988 driver is enabled. Sleep pin is active low input. Reset is also an active low input. The A4988 motor driver's output channels are broken out of the edge of the module with 1A, 1B, 2A, 2B pins. Now we will discuss 4x4 keypad. 4x4 keypad has total of 8 connections where 4 of them are connected to the column and the remaining rows of the matrix of switches. When an individual button is pressed, a connection is established between one of the rows and columns. Pressing a button closes the switch between a column and a row trace, allowing the current to flow between a column pin and a row pin. Now we will discuss IR sensor. And IR sensor is a radiation sensitive component with a spectral sensitivity in the infrared wavelength range from 780 nm to 50 micro m and IR sensor can measure the heat of an object as well as detects the motion. The emitter is simply an IR LED light emitting diode, and the detector is simply an IR photodiode. Once it is used as a combination of an IR transmitter and receiver, then the receiver's wavelength must equal the transmitter. Here the transmitter is IR LED whereas the receiver is IR photodiode. In picture we can see IR sensor has 3 pin VCC, ground and output. Now we have 16 by 2 LCD display. A 16 by 2 LCD display is very basic module and is very commonly used in various devices and circuits. A 16 by 2 LCD means it can display 16 characters per line, and there are two such lines. 16 by 2 LCD has two registers, namely command and data. Command register stores various commands given to display. Data register stores data to be displayed. 16 by 2 intelligent alphanumeric dot matrix display is capable of displaying 224 different characters and symbols.
Here is the circuit schematic for tachometer. It has two parts. One is the input part and the other one is the output part. First we will discuss the input part. In the input part, we will use a Tiva C series Launchpad, an Arduino to power the Launchpad, a potentiometer to give input speed and varies it as required. And then we use a stepper motor, a motor driver A4988 battery to power the stepper motor. As user gave input via potentiometer, the motor driver reads and then the stepper motor runs. This is all about the input part. Now we will discuss about output part. Output part, we use a Tiva C series Launchpad, Arduino as a power source and IR sensor which is used to read speed of motor and displayed it on LCD. Here we use a potentiometer which is used to setting the contrast of the LCD. Here we also interface a push button which is used to switch between RPM and radian per second, not for all connections.
This is a function we use to run and control the speed of the stepper motor using a potentiometer. In the first step, we define the step pins. For example, the step pin is used on the port 12 of Tiva, direction pin is on the port 13 of Tiva, and analog pin is on port 10. Then we define the variables custom delay and custom delay mapped. In the void setup function, we define the pin modes. Step pin is used in output mode. It tells the stepper motor how many steps it has to run in one revolution. Direction pin is also used in output mode and it tells the stepper motor the direction it has to run. High is used for clockwise direction while low is used for anti-clockwise direction. The analog pin is used in input mode. It gets the value from the potentiometer and uses it in the function to control the speed of the stepper motor. We digitally write direction pin high so that the stepper motor runs in clockwise direction. In void loop, we first use the function speedup function. Now we'll go on the speedup function to see what it does. In this speedup function, we first define the variable j equal to 0. Then we put the value we get from the potentiometer into the custom delay variable. The value of the custom delay variable is then used to in the map function. We put the value in the j variable by mapping the custom delay value from the potentiometer. 8-bit analog inputs can range from 0 to 1, 10, 23. Now we map the values 300 to 4000 to get the delay. Then we return the j value, which means that the value that will be mapped from 3000 to 4000 will be returned. After getting the value from map from 300 to 4000, print the value in the serial monitor. Then we digitally write the stepper pin high, which means that now the step has to perform. Then we put a micro delay of from the mapping of the value that we get from the potentiometer. The custom delayed value is in microseconds. The delay will be in microseconds, which is a very small value, but it will create a bigger difference in the controlling the speed of the stepper motor. If the value is high, the delay value is high, the speed of the potential stepper motor will be very low, and if the value is low, the speed of the stepper motor will be very high. Then we again write the stepper function step pin low so that another step is performed. Then we put the delay again. So this means that once a step will be performed, then there will be a delay, then again a step will be performed, and then there will be a delay. Overall, this is very difficult to see from the naked eye, but it will create a bigger difference in controlling the speed of the stepper motor. This is how we control the speed of the stepper motor using a potentiometer. Assalamualaikum. Here is the IR sensor code that I've written. Our IR sensor, it detects the RPM from our stepper motor and then it displays it on an LCD screen. For the LCD, I've used the liquid crystal library. This is available on Energia. These are the pins of the LCD that I'm connecting to our Tiva board. The IR sensor's output I've connected at PC5. I'm also using a button to swap between radian per second and RPM. One side of the button I've connected to PC6 and the other side I've grounded. I'm using negative logic for our button. Here is the liquid crystal function for our LCD. Then here is a user-defined function, RPM function. This function uses nested looping. It counts the number of zeros that are coming from our IR sensor and then it returns the count. Here is the setup function. First of all, I display an introductory message, digital tachometer on our screen. And here I have declared some of our pins. The IR sensor is declared as an input pin. And for the button state, I have connected an internal pull-up resistor since we're connecting our button in negative logic. Here is the main void loop, which runs again and again. First of all, I'm declaring some variables here, RPM and radian per second. Then I clear my screen. And here I am displaying reading RPM to show the user that the program is calculating RPM in the background. The RPM function, this is the main formula that I'm using. This formula you'll have to write by yourself. You'll have to read how many times your motor turns in 1 minute. You'll have to record that. And this also depends on your microcontroller speed. So this formula will depend on your microcontroller and the motor you're using. After that, I clear my screen and I show the RPM over here. I've put some delay over here. And after that, if the button is pressed, I'm using a condition here that if the button is pressed, 1, the LCD, it displays the speed in radian per second. Here, it calculates the radian per second as RPM times 2 pi by 60. And then it delays, there's a delay, and then it clears the screen.
This is the final working model of our project, which consists of 2 boxes, input and motor part and the output part. The speed of the motor is controlled by the potentiometer attached to the box. The shaft of the motor is faced toward the sensor, and the sensor then detects at the speed of the shaft and displays it on the LCD display in RPM or radian per second according to the user's choice. And that brings us to the end. Thank you so much for watching.